The geometric series is a really important tool in our toolbox of series to know about. So let's do one example of it real quick. What is a half plus a half squared plus a half cubed plus etc.? Well, let's write out the decimals. So a half is a half. 0.5 squared is 0.25. 0.5 cubed is 0.125. 0.5 to the fourth is 0.0625. Or we could write it out as fractions, right? We could write 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... What do you think that all adds up to? There's an interesting way to draw what's going on. Let's draw a pie kind of circle. Let's say this first side is a half, fairly uncontroversial, and then this next part is a fourth, and then let's cut the remaining fourth in half. That's 1/8, and then cut the remaining 1/8 in half. That would be 1/16, etc. So each time we're adding a new term, we're saying cut the remaining part in half and add that. So what's this going to add up to? Well, the whole circle would be 1.0 or 100%. So this is an interesting demonstration that adding an infinite number of numbers can end up giving you a finite answer rather than giving you an infinite answer. What are the partial sums? Let's take a look at that real quick. So S, well, let's just say it's 0.5 and then 0.75, a half plus a fourth, and then 0.825, a half plus a fourth plus an eighth, etc. So would we say this converges to 0 or converges to 1? Well, the sequence converges to 0. Right, these individual terms are getting smaller and will end up at, once you get to infinity, kind of at 0, but the series converges to 1. So remember, there's that distinction between does the sequence converge, does the series converge? Here they both converge, but they converge to different values. Let's write a general term for what's going on here. Can we say the sequence is 1/2 to the n? Does that sound reasonable? Like when n is 1, you get a half. When n is 2, you get 1/2 squared, which is a quarter. Or you could write it as 1/2 to the n. When you have a fraction to a power, that's like writing both the numerator and the denominator to that power, but 1 to the n is just 1, so we could write it that way. But this is starting at n equals 1, right? Which is kind of our default, but it turns out for other reasons it's better to start at 0 usually, and so that's what we'll do when we're defining the geometric series. So let's do that next. So we're going to say it's some for some constant value r. We're going to say r to the 0 plus r to the 1 plus r to the 2 plus r to the 3 plus ... So up above here we have r equals a half, but it doesn't always have to be a half. And how would we write this with a summation notation? We'd say r to the n, and here n starts at 0. It just makes the formula that we get nicer if we start at 0. So up here, n equals a half, or r equals a half. But we started at n equals 1 rather than n equals 0. Let's think real quick, how does the geometric series behave? What do the partial sums do for different values of r? So let's say at r equals 1.1, I think we did this on the Excel sheet, the partial sums grow exponentially. So that's our partial sums. I guess we could say s sub n. At r equals 0.9, the partial sums grew but kind of leveled off. At r equals negative something like 0.9, the partial sums did this. And at r equals like negative 1.1, the partial sums do that. So in which of these cases would you say that the series converges, that the limit of the partial sums as n goes to infinity is a finite number, not running away to infinity, not oscillating without settling down? I'd say the series converges here. Here the series diverges by running away to infinity. And here the series diverges by oscillating without settling down. In fact, not just oscillating without settling down, but oscillating more and more at each step. So based on this, hopefully it's plausible that we can say when does the geometric series converge and when does the geometric series not converge. And that's called the geometric series test, which is the geometric series converges when the absolute value of r is less than 1. Is that true here? The absolute value of r is less than 1, absolute value of r is less than 1. You could also write this as negative 1 is less than r is less than positive 1. And the geometric series diverges if the absolute value of r is bigger than or equal to 1. If r is equal to 1, then you're just doing 1 plus 1 plus 1 plus 1 plus 1, and that'll be growing linearly to infinity. If r is negative 1, then you're doing plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, and that oscillates without settling down. And when the geometric series converges, what does it converge to? And it turns out it's a fairly nice formula, 1 over 1 minus r. So we could say, what does this series with a half converge to? It would converge to 1 over 1 minus a half. 1 minus a half is a half. 1 over a half is 2. But here we got that it was the series was converging to 1. What's the discrepancy there? Well, here we were starting at n equals 1. We were starting with a half plus a fourth plus an eighth. The definition of geometric series is starting at r to the 0, and so that would mean we should start at a half to the 0, which is 1. So we go 1 plus a half plus a fourth plus an eighth plus a 16th. So that would add up to this whole pi plus another whole pi over here for just the 1 term. So that's how we would get the 2.